Hello friends, welcome to SuperProfs. The course which we are studying is Digital Electronics and this is lecture 2 on logic gates. My name is Abhishek Gupta. In the previous lecture we have studied number systems, different types of number systems like octal number system, decimal number system, hexadecimal number system, binary system, and we have also seen the sum of the complements. In this lecture we are going to see what is the logic gates, what are different types of logic gates possible and what are their properties. So let's start with first logic gate, and in this we are going to discuss first introduction. So what is logic gate? See, logic gates are the most fundamental digital circuit, because every digital circuit, mark this point, the most fundamental digital circuit, because every digital circuit is derived from these logic gates only. So we can say that these are the most fundamental digital circuits. The boolean 0 and 1 represents logic level. We can say that a boolean 0 and 1 represents logic level. What is mean by logic level? See, in analog circuits, what we have discussed, or what we see, that plus 5 volts and 0 volts are the main voltage levels we are operating on. So if we are converting the analog system into a digital one, we are representing positive 5 voltage as logic 1 and 0 voltage as logic 0. Okay, so these are some of the representations so that we can make an analogy between the analog circuits and as well as the digital circuits. So we can see that in this table, logic 0 is holding for false condition. If any condition is in false nature, then the logic 0 will be applied. If any switching circuit is in off condition, then also we take it as logic 0 or boolean 0. If it is low input or low output, then also we take it as logic 0. If the system is giving a no operation or the condition is not fulfilled, then also we use it as logic 0 representation. And logic 0 is also valid for open switch, like when we discuss the switching circuits, in the open switch the logic 0 is applied. Similarly, if we can see logic level 1, it is holding true condition, on condition, high condition, yes condition, as well as close condition, like close switch. So you can make this table logic 0 and logic 1. Now we come to the point where that is truth table. So what is truth table? First of all, we will see the definition. Truth table stands for describing how a logic circuit output depends on the logic levels present at the circuit inputs. So students, what it means, that depending on the logic inputs, like what we are giving the logic, like logic 1, logic 0, or both 0 1 1 0, depending on that how our output is changing, that describes our truth table. So definition is, it is a means of describing a logic circuit output depends on the logic levels present at the circuit input. So we can say that on the basis of input we are getting the output, and the representation of such cases is represented in truth table. So fourth point, that is number of input combination is 2 raised to power n for n inputs. What it means, students? See, if we consider an example in which there are 2 inputs, okay, 2 inputs which are x and y. Okay, so possible combinations of 0 1 or logic 0 logic 1 are 0 0, it can be both 0, or it can be 0 1, it can be 1 0, or it can be 1 1. Okay, so we can say that there are 4 types of possible combinations: 0 0, 0 1, 1 0, and 1 1. So we can say that for n combinations, as there are 2 inputs, there are 4 combinations. So we can say that if there are n combinations, there are 2 raised to power n inputs, or we can, if there are n inputs, there are 2 raised to power n combinations. So if we keep n is equals to 3, the combinations that we are getting, students, would be 2 raised to power 3, that is 8 combinations. So when we discuss about full adder, we will see that how many combinations are possible. So moving ahead, we are going to see logic gates can be classified as basic gates. In basic gates, there are 3 type of gates. First is NOT gate, second is OR gate, and third is AND gate. Okay, and the second type of gates are universal gates, that are NAND gate and NOR gate. Why we are calling NAND gate and NOR gates as a universal gate, students? Because from NAND and NOR gates we can derive any kind of gates. So we will also going to see what are the possible structures or circuits, so that we can make AND gate or different types of gates using NAND and NOR gates. And there are the third kind of gates, which is special purpose gates. First is XOR gate and second is XNOR gate. So it is a combination of AND and OR conditions. So we are going to see why they are called special purpose gates. Now first we will start with NOT gate. So what is NOT gate? First of all, we should understand what is NOT gate and what would be the output of a NOT gate. So before starting with a NOT gate, we should know what is buffer. So if we are having a buffer, for the symbol for buffer is like this, and if the input is X, the output is also X. But for the NOT gate, if the input is X, the output would be X of complement, matlab X ka complement. So we can say that NOT gate is a complement of buffer gate. So this is the sign for complement. So first we are going to see what is the symbol of NOT gate. So we are going to draw the symbol. This is the symbol, students. This is the sign for buffer, and we want to take its complement. So this is the complement. So if we are giving the input X, the output would be X bar. Okay, this is the output. Now we can represent it in another way. If the input is this, first we are doing the complement, then we are taking through its buffer. So the output would also be same X, and the output would be X bar, that is X of complement. Okay, so this is symbol. Now we are going to see what would be its truth table. So we know, students, what is truth table. Truth table stands for the truth table stands for means that so that how the output is depending on the number of inputs. So if there is a one input, there are only 2 possible combinations. So if X is the input and the output would be let us consider Y, which is X bar. Okay, so number of inputs possible, students, would be 0 and 1. Okay, 0 and 1 are the possible combinations. So output would be its complement, that is 1 and 0. Okay, this is the symbol and the truth table. Okay, now we are going to discuss what would be its switching circuit. So what do you mean by switching circuit? We should understand we will apply a voltage level. Okay, we are applying a voltage and we are connecting a bulb through this voltage level. Okay, now we have to construct such a circuit so that it can represent a NOT gate. We have to use some of the switches present and we have to make it work as a NOT gate. So let us discuss what would be its switching circuit. See, there is a voltage level. This is the voltage level V, and this is our bulb. Okay, this is our bulb. Now we have to place a switch X in such a way that it can resemble or it can be a working of a NOT gate. So for a complement, remember, students, the switch will always come in parallel with the bulb. So let us apply a switch X which is in parallel with the bulb. So this is bulb. Now we can see that if the switch is closed, that is if the switch is having the logic 1, then the bulb would get short circuited and the output for the bulb would be 0. that is bulb would be off, in the off condition. It means that the output would be 0. So we can see that this condition is fulfilled when the logic X is 1, that is the switch is in closed condition, the bulb would be in off condition. Okay, and if the bulb is in open condition, that means it is open circuit. If the switch is open circuit, which is representing logic 0, the bulb would be in on condition, that is in logic 1 condition. Okay, because the current would flow like this. Okay, this is voltage level. So we can say see that this switching circuit is fulfilling the NOT gate. So this is the representation or the switching circuit for the NOT gate. Now the fourth point would be its transistor circuit. So how we are going to draw its transistor circuit? See students. So we are going to draw transistor circuit. For the transistor circuit, we are using an Npn transistor, and very basics of Npn transistor would be used. So no much knowledge is required to know the working of a Npn transistor. What is required, I would explain in this circuit only. Okay, so see. We are constructing an Npn transistor. This is an Npn transistor. We are applying ground voltage. This is our base. Okay, and we are giving is an input X. Okay, now at collector there is a voltage level plus VCC, and the output that we are taking would be from this, that would be Y, which is equals to X bar. So this is an Npn transistor. Okay, this is also a resistor, we can say this is R. Okay, we have applied the input at X and we are taking an output at Y, and now we are going to see this is transistor T1. Now we are going to see its truth table. Okay, this is X input, this is transistor T1, and this is Y as our output, which is X bar. So see, the input combinations are 0 and 1. So if we are giving the input as 0, that is ground voltage, the transistor would be in off condition, students. So we are giving off condition. So transistor is off. As the transistor is off, there would be no flow of current through collector and towards emitter. So there would be no voltage drop in this resistor, due to which this voltage would appear at this point Y, and we can say the output would be logic 1, that is plus VCC. See, this is so much simple in nature. Okay, now we are applying logic 1. What is logic 1? We are applying a positive voltage on the base side, due to which the transistor would be in on condition. And now as the transistor is in on condition, there would be a flow of current, and if we are considering as an ideal transistor, this ground voltage would appear at this point and the output would be 0, or we can say that it is a ground condition. So we can say that this circuit or this transistor circuit is fulfilling, or it is representing a NOT gate. Okay students, so we can see the symbol, the truth table, the switching circuit, and as well as its transistor circuit. So you can draw, and you can also write one point, that is NOT gate is the complement of buffer. Okay, is a complement of buffer. So quickly write these points. Next we are going to see the properties of NOT gate. I hope students you are able to understand these properties, because it is quite simple in nature, and up to second or third lecture there would be very simple properties as that are being studied in number systems, and we are going to see logic gates. These are some simple, but their questions are quite tricky. So when we are going to solve the problem solving sessions after the completion of logic gates, you will see how important and some of the good questions on the logic gates. So I hope you have written the points on the NOT gate. Now we are going to see some of the properties of NOT gate. So first point is even number of NOT gates. You can see this is the first point. Even number of NOT gates in series will act as a buffer. What it means, students? Now first consider even number of NOT gates. So we are taking two NOT gate. Okay, so if we are giving an input x here, the output would be x bar, and after this the output would be x of double bar. It means x. So we can see what the input is x and the output is also x. So the even number of NOT gates is working as what? It is working as a buffer. So see, even number of NOT gates in series is working as a buffer. Now second point is even number of NOT gates with feedback would work as a bistable multi-vibrator. Now we are going to see how it would work. Consider two NOT gates. Okay, now we are connecting it through a feedback. Okay, so if we are giving input x, this would be x bar and this would be x double bar. So this was the journal input. Now we are going to try with some 0 and 1s. So if we are given here 0 as an input, it would be get converted into 1, and after this would be converted into 0. Now this 0 would be feedback again as an input, and it would always remain 0 as an output. So we can say one stable state is equals to 0. Okay, so one stable state is 0. Now if we give input as 1, okay, if we are giving input as 1, the output from first NOT gate would be 0 and the output from second NOT gate would be 1. This one would get again feedback towards the input, and due to the stable nature, the other stable state would be 1. Okay, so we can see that there are two stable states, 0 and 1. Therefore, the name is bistable multi-vibrator. Okay, so we can see why we are saying that this circuit with even number of NOT gates with feedback is working as a bistable multi-vibrator, because there are two stable states and there would be no change in states until and unless we are changing the output. If we are giving continuously 0, the output would remain always 0, and if we are continuously giving 1, the output would always remain as a 1 until and unless we change the output from 0 to 1 or 1 to 0. Okay, now third point is odd number of NOT gates with feedback. So now we are drawing odd number of NOT gates. These are odd number of NOT gates. Let us take an example with 3 NOT gates. These are 3 NOT gates, and this is our feedback. Okay, this is our feedback. So let us consider with example only. If we are considering an example of 0 as input, the output would be 1, this would be again 0, and this would be again 1. Now 1 will go as a feedback to the input, and this would be changed at 1, this would be changed to 0, this would be changed to 1, and this would be changed to 0 again. Now 0 would go into the feedback and it would again change to 0, this would again change to 1, this would again change to 0, and this would again change to 1. So students, we can see that there is a change in the input from input as well as output from 0 to 1, 1 to 0, 0, 1, 1, 0. Therefore there is no stable state as well, so we can say it is a stable multi-vibrator. It can also be known as square wave generator or clock generator or ring generator, because if we draw the clock pulse of this, if we draw the pulse of this output, we can see that it is changing from 0 to 1 to 0 to 1 to 0 to 1 to 0 and so on. So this is also known as the clock pulse. So therefore we can say a stable multi-vibrator, which is a combination of odd NOT gates with feedback, also works as a clock pulse generator. Okay. But what would be its time period? We have to calculate what should be its time period. अब इसका time period क्या होना चाहिए? Okay, so we are going to see what would be its time period T. So we know that all inverters would take some time to respond. See, no inverter is ideal in nature. In every inverter there would be some delay in giving the output, and the output would be, and the time taken by the NOT gate would be known as propagation time delay. So we are saying, and all inverters take some time to respond, which is equals to the propagation time delay, or we can represent it as TPD. So for a stable multivibrator, time period would be, if we are considering three inputs, see, there are three NOT gates. Okay, so the delay would be 3 TPD in generating one output. So we can say this 0 level would be 3 TPD. Okay, and in changing from 0 to 1, it would take around 3 TPD time, or 3 into propagation time delay. Okay, therefore the time period for three NOT gates will be T is equals to 6 TPD, or if we are learning in a general way, we can say that the time period would be T is equals to 2 into N into TPD, where N stands for number of NOT gates. Okay students, so these are some points regarding the NOT gate. First point was even number of NOT gates in series would be buffer. Second point would be even number of NOT gates with feedback would represent as bistable multivibrator. Third point is odd number of NOT gates with feedback, it would be equals to a stable multivibrator, or we can say that clock pulse generator, and its time period would be 2 into N into TPD, where TPD stands for propagation time delay, and stands for the number of NOT gates, and T would be, capital T would be time period. So quickly write these points. Next we are going to see one example related to the NOT gates. So this is very important point regarding the exam point of view. What should be the time period of the connection of NOT gates with feedback? So the time period would be 2 into N into TPD. Okay students, now we are going to see one example related to the connection. See, in the circuit, the propagation delay of each NOT gate is 2 nanoseconds. The time period of generated square wave is, so the propagation delay for each NOT gate is given as 2 nanoseconds. Okay, there are 4 NOT gates connected in this way, and there is a feedback after the third NOT gate. So we have to calculate the time period of the generated square wave. First, students, write yourself what would be the answer. Then I would explain what should be the answer. Okay. We know the formula T is equals to 2 into N into TPD. So just we have to know what should be the N. If we are able to understand what should be the N, we are going to calculate its time period also. So the main point that we should understand how to know what would be the value of N, or what would be the number of NOT gates through which we are generating the clock pulse. So students, let's try it. We can see that after the 3 NOT gates we are able to give the feedback. So if we are giving here 0, this is 1, this is 0, this is 1, and from this we are getting the feedback. This is 1, this is 0, this is 1, this is 0. So students, what the number of NOT gates which are required to generate a clock pulse is 3. So we can write like N is equals to 3. So what would be its time period? 2 into 3 into 2 nanoseconds. So it would be 12 nanoseconds. The answer is 12 nanoseconds, but the point is not the answer. We have to understand what this 4th NOT gate is doing. Okay, so what is the purpose of the 4th NOT gate? The 4th NOT gate, or we can say the last inverter which is connected, is just used to make a delay of 2 nanoseconds in the generated clock pulse. What it means, students, see, we are able to generate a clock pulse like this. Okay, this is our clock pulse after this NOT gate. So this is what is 6 TPD, and this would also be, this would be like completely write it, this would be 12 nanoseconds, and this would also be 12 nanoseconds. So sorry, this would be 6 nanoseconds, 6 and 6. So the complete time period would be 12 nanoseconds. Okay, so after the last inverter, what would be our output? There would be a delay of 2 nanoseconds. So if we are taking it as 2 nanoseconds, the output would be like this. Okay, this is our delay which are caused due to the 4th inverter. So the 3 inverters is used to generate the clock pulse, and the 4th inverter, students, is used to generate the delay of 2 nanoseconds in our clock pulse. So this is the answer, which is 12 nanoseconds. Okay, quickly write this example, and then we are moving towards next gate, which is AND gate. This is 6 nanoseconds, and this is also 6 nanoseconds, and there would be a delay of, there is a delay of 2 nanoseconds. Okay, So now we are going to move towards the AND gate. So what would be the symbol? The 4 points that we are discussing in all the gates would be symbol, its truth table, its switching circuit, as well as its transistor circuit. So first we are going to see what is the symbol. So symbol, we all know what is the symbol of AND gate. See, there are two inputs X and Y, and there is a symbol of AND gate, and the output is X dot Y. Okay, so what it means, X dot Y means, like, what is the meaning of X dot Y? So it means that if both the inputs are logic 1 or in high level, then only the output would be in logic high level or logic 1. Unless अगर कोई भी input, if any of the input is in 0 level, the output would be 0 level. So we can say that by knowing the truth table. See, this is our truth table for this AND gate. So there are two possible inputs X and Y, and the output X dot Y would be 0 0 0 1 1 0 1 1. Okay, so 0 0 0 1 1 0 1 1 are the possible combinations. So due to 0 0, the output would be 0 0 1, output would also be 0 1 0, the output would remain as 0, and for 1 1 input, the output would be 1. So we can say that for the AND gate, if both the inputs are in logic high level, then only the output would be in logic high level. So this is the truth table and the symbol for the AND gate. Now we are going to discuss its switching circuit. So in switching circuit, what we are going to discuss, how to switch on the bulb and what are the conditions. So if this is a voltage level V, this is a voltage level V, and there is a bulb connected like this. Okay, so this is our bulb. Now we have to see that what should be the connection possible to represent an AND gate. So if we take the hint from truth table, we can see that if both the logics are 1, then only the output would be 1. So comparing through the switching circuit, we have to place the switches in such a way when both the switches are in closed condition, then only the bulb would be in on condition. So let us try to connect in series connection. So we have connected two switches X and Y, and the bulb is like this. So try to understand through the truth table. If the inputs is 0 0, that means if the switches is in off condition, then the bulb would be off. Okay, because there would be no flow of current, students. If any one of the switches in off condition, like see in 0 1 and 1 0 conditions, if any of the switches is in off condition, the output would also remain the off, because there would also be no off current in that case also. But if both the inputs is in 1 1 condition, that means both the switches is in off condition. Sorry, if both the switches is in on condition, then the bulb would be in on condition, because there would be a flow of current like this. So we can say that this switching circuit or the connection in series of two switches represents our AND gate. So this is our AND gate. Now we are going to see the transistor circuit for AND gate. Okay, students, so first we are going to draw two transistors. This is one transistor, okay, and another transistor would be this. This is ground, this is base, two bases for the two transistor, as input X for one transistor and input Y for another transistor. Okay, this is our collector, this is another resistor, this is plus VCC, this is our T1 and this is our T2. Okay, and from where we are taking the output? We are taking the output from this point. So let us take it Z, which is X dot Y. Now we are going to see its truth table, students. So try its truth table. This is X, this is Y, this is T1, this is T2, and this is our output X dot Y. Okay, so let give the input 0 0 0 1 1 0 1 1. Okay, if any one of the inputs or both the inputs is in off condition, that is 0 0. If any of the inputs to the base is 0 or low logic or ground, the transistors would be off. So in this case both the transistors are off. In this case T1 is off, T2 is on. In this case T1 is on but T2 is off, and in the last case both would be in on condition. So if any one of the transistors is in off condition, there would be no flow of current. Okay, due to which this ground voltage would be appeared at this point Z. Therefore the output would be 0 0 0, or we can say ground condition. Okay, but if both the inputs are 1, that is logic 1 or logic high level, so both the transistors would be in on condition and there would be a flow of current. And if we are considering as an ideal transistor, there would be output as 1, which is plus VCC. So this is the representation through symbol, truth table, switching circuit and transistor circuit for the AND gate. There is one circuit also possible, we are going to discuss here only, which is diode circuit diagram. So in diode circuit diagram we have to represent the AND gate. So let us connect the diodes. Okay, we are connecting the diodes like this, and this is our plus VCC voltage. Okay, we are taking the output from here, which is Y, and the inputs are A and B. Okay, and this is D1 diode and this is D2 diode. Okay, so this is A dot B. So from the truth table we can see that if both the inputs, if any one of the inputs or both the inputs are in 0 condition, that means if A and B are in ground condition, then D1 and D2 would be forward bias, or we can say in on condition. So the voltage level at A or B would be reflected at this point, which is Y, and the output would be same. So if the input is 0 and this is also 0, this would be D1 and D2 would be forward bias, and this voltage would be appeared at Y. So the output would be 0 0 0. But if both the inputs are 1 1, that is this is also 1 and this is also 1, that means we are applying a high voltage on the reverse bias side. So we can say that D1 and D2 would be reverse bias in nature, as the both diodes D1 and D2 are in reverse bias nature. The both diodes D1 and D2 would be in off condition, so there would be no flow of current, and this plus VCC voltage would be appeared at this point, and the output would be 1, that is plus VCC. So this diode circuit diagram is also representing the AND gate. So students, what we have discussed about AND gate: first is symbol, second is truth table, third is switching circuit, fourth is transistor circuit, and fifth is diode circuit diagram. So you can quickly write these points with the explanation also, and then we are going to move towards the OR gate. So symbol, truth table, switching circuit, transistor circuit, and diode circuit diagram. Okay, now we are going to see our next gate, which is OR gate. So for OR gate also we are going to see first symbol. So what is the symbol of OR gate? We all know, students, if the inputs are X and Y, so this is the symbol for OR gate, and the output would be X plus Y. Okay, now what would be its truth table? This X plus Y, students, is the logical addition. Okay, students, what you mean by logical addition? That if the inputs are 1 1, the output is 1. But in arithmetic addition, what we are going to do in combination circuits, in arithmetic addition, 1 plus 1 is equals to 0 at sum, and 1 would be carry. So this is not arithmetic addition, this is a logical addition. So if we are giving inputs as 1 and 1, the output would also be 1. So we are going to see the truth table for this. If the number of possible conditions are 0 0, 0 1, 1 0, and 1 1, so output would be X plus Y. So 0 0 would be 0. Now if any of the inputs is logic high level or 1 logic 1, the output would also be 1. So the outputs for 0 1 is 1, 1 0 is also 1, and 1 1 is also 1. It means if any of the logic level is in high condition, the output would also be high. So this is our symbol, and second is truth table. Now third, we are going to discuss its switching circuit. So to understand what should be switching circuit, we would take the help of the truth table. In the truth table, we are able to understand that if any of the switches is in on condition, then the bulb would be on. Okay, so what should be the connection, students? It would be connected in parallel. So this is our bulb, and this is the parallel connection of the switches. This is X, this is Y. Okay, this is our voltage level. So if both the inputs are 0 0, that means both the switches is in off condition, then the bulb would remain off. But if any of the switches, like in second condition 0 1, the X switch is in off condition, but 1, that is Y, would be in on condition. Therefore the bulb would be in on nature, because there is a flow of current through the Y switch. But if both the switches are in on condition like this, then also the bulb would be in on condition, because the current would pass through this, and we are getting the current through the bulb, and the bulb would be in on condition. So this is the switching circuit for the OR gate. Now we are going to discuss its transistor circuit. So similarly, same as switching circuit, the transistor circuit would be the parallel combination of what? Transistors. So quickly we are representing the switching circuit. We are here taking two transistors which is in parallel condition. So these are two transistors, okay, and this is plus VCC, this is transistor T1, and this is transistor T2, and this is resistance R, and this is ground, and output we are taking from this point, that is Z is equals to X plus Y. Okay, so if we want to draw its truth table, students, this is X, this is Y, this is T1 transistor, this is T2 transistor, and output would be Z. So 0 0 0 1 1 0 1 1. Okay, so in for 0 0 condition, the T1 transistor and T2 transistor would be off, and for 0 1 T1 would be off and T2 would be on. For 1 0 T1 would be on, T2 would be off, and for 1 1 both the transistors would be in on condition. As both the transistors would be in on condition, there would be a flow of current, and this voltage would become plus VCC, that is 1 is equals to plus VCC. But if any of the inputs is in one condition, that is if any of the transistor is in on condition, then also there would be a flow of current, due to which the output would remain as 1, logic 1, or we can say plus VCC. Okay, but as both the transistors are in off condition for logic 0 0, then there would be no flow of current, and due to which this voltage would appear at this point. Therefore the output would be ground, that is logic 0. So this is our symbol, truth table, switching circuit and transistor circuit. The fifth point we are going to see is its diode circuit diagram. So for diode circuit diagram, what should be its diode circuit diagram? See students, we are connecting the diode or in parallel condition also. So if this is input A, let us take the input A and B. This is input B. Okay, they are connected in parallel, and output is taken as here, which is Y A plus B. Okay, so if any of the diodes is forward bias, the output would be 1. That is, if A is 1 and B is 1, both the diodes would be in on condition, then output would be Y. But if both the diodes are in off condition, that is 0 0, the output would remain 0. Okay, so this circuit is representing our OR gate. So first is the symbol, second is the truth table, third is the switching circuit, fourth is the transistor circuit, and fifth was diode circuit diagram. So quickly write these points. Next we are going to see another gate. Okay. So the important point for OR gate was that it is a logical addition, not arithmetic addition. Here you can see it is not arithmetic addition. Okay, it is logical addition, in which 1 plus 1 equals to 1. Okay, so this was AND gate and OR gate. Now we are going to see one example related to AND gate and OR gate. So we can read this example. If a function f is logic 0, it means function f, the output is 0, then maximum number of possible minterms in the function f3 is, हमें f3 के number of possible minterms पूछे हैं. So we have been given f1 as sigma 2 3 4 minterms 2 3 4, and for f2 we have been giving the max terms, that is 0 1 3 5 7. As we have to calculate the possible minterms, we are converting into the minterms would be sigma 0 1 2 4 5. So these are the possible minterms for the function f2. So as we can see that this function f1, f2 and f3 is the AND operation, is going through the AND operation. Therefore we have to take only the common terms or the common minterms that are present in all f1, f2 and f3. So first we are going to see what should be the common minterms in f1 dot f2. So we are able to understand that in the AND gate we are able to get only the common minterms, that is the intersection of both f1 and f2. So f1 and f2 की common terms would be sigma, देखो minterms 2, 3, 4 and 2, 4, 5. So the common minterms would be 2, 4. Okay. Now we have to take f3 such that the output would be f is equals to 0. So f3 should be such that when we take the common minterms in 2 and 4 and the minterms in f3, there should be no common terms. Okay, so what are the possible minterms that can be in f3 function? 0, 1, 3 and 5, 6 and 7. So these are the possible minterms that are can be presented in function f3, because there would be no common minterms, therefore the output would remain 0. But instead अगर ऐसा होता, if there is an OR gate, then we are going to take all the minterms present in f1, f2 and f3. Okay. So this is our answer, which is f3. The minterms are 0, 1, 3, 5, 6 and 7. Okay students, so this was the example. Now we are quickly going to discuss NAND gate. So first point regarding NAND gate is, it is the complement of AND gate. So through this we are going to derive all the possible things like symbol as well as its truth table as well as its transistor circuit. So first we are going to see symbol. So we know as the NAND gate is the complement of AND gate. So if there are two inputs x and y, the output would be the complement of AND gate, that is x dot y whole bar. So this is the symbol for AND gate. Okay, this circle is used to complement the AND gate. Now we are going to discuss is truth table. So what should be its truth table, students? If the x and y are the inputs and x dot y bar is the output, so 0 0 0 1 1 0 1 1 are the possible combinations at the input level. The output would be 0 0, the AND gate output would be 0, but its complement, then the output would be 1. Similarly for this it would also be 1, for this also 1, but for 1 1 the output for AND gate would be 1. But here in the NAND gate we are taking its complement, so the output would be 0. So we can say we can see the truth table for NAND gate. And the transistor circuit for NAND gate, students, see what should be the transistor circuit. So for transistor circuit we are connecting the transistors similarly to the AND gate connection. This is X, this is Y. Okay, this is our T1 transistor and this is our T2 transistor. Okay, this is our ground. So this is plus VCC at collector, this is our resistor and this is our connection. So in AND gate we have taken the output from this point, but in the NAND gate we are taking the output from this point, that is x dot y bar. Okay, so if we want to make its truth table, now let us understand what should be its truth table. So this is XY, and this would be T1 transistor, this is T2 transistor, and this is our output. Okay, so 0 0 0 1 1 0 1 1. So quickly write its conditions for T1 and T2. This would be off, this would be off, this would be off, and this would be on, this would be on, this would be off, and for 1 1 both the transistors would be in on condition. As both, so first we are going to see 0 0 condition. So in the transistor circuit we can see that if both the inputs are 0, that both the transistors would be in off condition, due to which there would be no flow of current, and this plus VCC voltage would appear at this point, because there would be no voltage drop at this resistor. So the output would be 1, or we can say that plus VCC. Similarly here also plus VCC, here also plus VCC, because in any one of the transistors is in off condition. But for 1 1 condition both the transistors is in on condition, so there would be a flow of current, and at this point the output or the voltage would be 0, that is ground, if we are considering the both transistors is in ideal nature. So we can say that this transistor circuit is representing the NAND gate. So in the AND gate we have taken the output from this point, but in the NAND gate we are taking the output from this point. Okay, so now quickly we are going to discuss about its switching circuit also. What should be the switching circuit? As it is the complement of AND gate, therefore the connections would be the connections of the switches would be in series nature. But as it is the complement of AND gate, then therefore due to so that the series connection would be in the parallel to the bulb. So if this is our voltage V, so this is would be this switch would be X, and this switch would be Y. Okay, and this would be our bulb. This is our bulb. So we can see this is X, this is Y, this is voltage V. So through the switching circuit we can represent our NAND gate also. Here we can understand if both the switches is in on condition, that is both the switches are in closed circuit, that is closed switch. So there it would short circuit our bulb, and there would be no current through the bulb, and bulb would be in on condition. Therefore it is fulfilling our condition 4, that is both the switches are in on condition and the bulb is in off condition. But if any of the switches is in off condition, so there would be a flow of current through bulb, and the current bulb would be in on condition. So we can see that the NAND gate symbol, truth table, and transistor circuit and switching circuit as well. So quickly write these points. So students, I hope you have written these points. First is symbol, second is truth table, third is transistor circuit, and the fourth is switching circuit. So these are some points related to AND gate. In the next lecture, so students, in the next lecture we are going to discuss rest of the gates and some of the properties and the shortcuts related to these logic gates, and after that we are going to solve one problem solving session in which there would be some questions of previous year gate related to logic circuit, logic gates as well as number systems. Thank you.